Hey guys, we're going to get started on today's lesson. I am going to be working through your part 2 of the functions and continuity. So we're going to jump right in. Let me make myself a little smaller so you don't have to stare at me the whole time. And we're going to jump in with discrete and continuous. So I already defined them in the previous video. We're going to look at this again. Functions can be discrete, continuous, or neither. Real-world situations where only some numbers are reasonable are modeled by discrete functions. For example, a function that relates numbers of digital downloads and costs only makes sense for whole numbers of downloads. You're not going to download half a song. You want to download all of it. Situations where all real numbers are reasonable are modeled by continuous functions. A function that relates your distance traveled to time is continuous. You're not necessarily going to travel exactly a mile. You might go just a smidge past a mile. So this is a continuous function. Same thing with the time. The time is, you're not going to exactly travel 5 minutes. You might travel for 5 minutes and 22.2 seconds. So this is a continuous function. But if we're talking about download, how much it costs to download 3 songs. Each song costs 99 cents. So you're not going to download part of a song for 33 cents, a third of that song. That doesn't even make sense. So that would be a discrete function because one song is 99 cents. So 2 songs now cost 99 and 99 is $1.98. 3 songs would cost $1.98 plus 99 more cents. You get the idea. We keep on going. We've got $2.97 now. So we're going to just keep building. That's a discrete function, but continuous is like how long it takes me to walk from my home to the school. It's going to be there's continuous amount of time. Time is in minutes, seconds, milliseconds. I mean, you think about punching a stopwatch. It just continues and continues. All of the numbers are included. Okay, so we've got determining continuity of a function by examining the table or its graph. So we want to define these. This is in your workbook, by the way, on the bottom of page 5 if you're wanting to follow along. I would certainly be highlighting this so that it would be easy for me to find when I make my note cards at the end of the week or at the end of this lesson so that I can be studying these vocabulary terms. So a continuous function can be graphed with a line or an unbroken curve. A function that is not continuous is a discontinuous function. A discrete function is discontinuous function in which the points of the graph are not connected. So we've got a point, a point, a point, a point, but no line connecting them shows that it's discrete, and this is a discontinuous function. So we've got some definitions here. We know that the domain of a discrete function is the individual x values. It's not all of them, it's only specific ones. But on a continuous function, it is the interval of all the real numbers. And if it's neither discrete nor continuous, the domain is neither discrete nor continuous, varies, and may contain intervals of values and individual values. Okay, looking at the next part. Which of these are discrete, continuous, or neither discrete nor continuous? This one is discrete, obviously. We've got a bunch of random dots. Continuous, it goes on and on forever. And then neither discrete nor continuous. Part of it's continuous, then the other part's continuous, but there's a break, so we can't say this is just discrete or it's just continuous. It's a little bit of both. And again, we've got discrete, continuous, and neither discrete. A few more examples. Study tip here. Intervals. An interval is the set of all real numbers between two given numbers. So we've got this interval between -2 and 5. That can be any number in between. It can be a whole number, it can be a decimal, it could be a fraction, it could be a repeating decimal. This is numbers in between two values. So all of those are greater than -2 but less than 5 fall on that interval. You can use intervals to describe the values of x or y for which a function exists. All right, so let's look at some examples here. Determining continuity from graphs. I'm sorry for all the interruptions, guys. I don't know when I'm going to find a good time to video without there being speakers and people coming in and my phone ringing and all of that stuff. So you're just going to have to bear with me here. I'm sorry. Determine whether each function is discrete, continuous, or neither. Then state the domain and the range of each function. So it looks as if I have already completed this. The function is continuous because it's a curve with no breaks or discontinuities. Okay, let's look at the next one. Discrete or continuous or neither? Well, it looks like it's continuous until I zero in on this point right here. But then I can tell that right here, if you are following along with me on the mouse here, there is a break in the graph. And because of that break, we can say that it's neither discrete nor continuous, because there's a break at 2, 1. We can check it. Woohoo, we're right. And our next example. Discrete or continuous or neither? Of course, this is discrete because there's a bunch of random points. Our domain, our x values, are at -3, -2, -1. We don't have any at 0. 1, nothing at 2. We've got a point at 3 and a point down here on when x is 4. So that's my domain. My range is the corresponding y values. So I've got a y value of 1, 2, 3, 4. A y value of 3, a y value of 2, a y value of 1, a y value of -2, and a y value of -3. And notice they were listed in order from least to greatest. All right, so moving along to example 5, determine continuity. Gotta find a good place to put this. I'm not really having much luck yet. So if we're looking at continuity on this graph, it says a cafe sells coffee beans by weight. Move through the slides to determine whether the function that models the cost of coffee beans is discrete, continuous, or neither discrete nor continuous. Then state the domain and the range of the function. Remember, domain and range is just asking for my x and y values. So we've got weight up to 2 pounds, and the price is $8. Then my weight at 2.5 pounds is $20. My weight at 3 pounds is $22. My weight at 5 pounds is $35. So I'm automatically thinking, okay, discrete, because each weight has a different price. But then when I think about this up to 2 pounds, that means if I buy a pound, a half a pound, 3/4 a pound, 2 pounds, anything from 0 to 2 pounds, any amount in between is going to be $8. Something in that part is continuous. Then each one of these are discrete. So then that lets me know that my graph is going to be neither discrete nor continuous for the whole thing. But this part right here would be continuous over this interval from 0 to 2. It's a continuous function. So the function is continuous over the interval from 0 to 2. For larger quantities, it's sold by distinct amounts. Therefore, this part of the function is discrete. The domain and the range are made up of neither a single interval nor individual points. Therefore, the function is neither discrete nor continuous. Okay, and then so the domain of my function is all the values in between 0 to 2. And then it sells at exactly 2.5 pounds, 3 pounds, and 5 pounds. I guess you cannot buy 3.5 pounds or a 3.5 pound bag or a 4 pound bag or a 4.5 pound bag. They only sell it up to 2 pounds, then exactly 2.5 pounds, then exactly 3 pounds, and then exactly 5 pounds. So that is my domain. And my range is each of these corresponding y values. So my range could be $8 per pound up to 2 pounds, or it could be $20, $22, $35. So this says that the range of the function is 0 to 16. It could be 0, it could be 16 including, and all the values in between. So I guess what they would do is take since it's $8 per pound, they would take the price, $8, and divide, let's say I buy 1.5 pounds, they would do 8 divided by 1.5, and that could be my price. So it would be anything between 0 and 16. All right, I like these problem-solving tips here. Just to kind of give you a visual for what this is saying, any amount of coffee beans that I buy in between 0 and 2 pounds, I'm going to have a different amount because it's $8 per pound. So they're going to take that $8 and divide it by the weight that I get, and I get the corresponding value. So it looks like my graph is continuous over this interval. Then it just it's broken up into discrete points. If I buy a 2.5 pound bag, it's automatically $20. I buy a 3 pound bag, it's automatically $22. I buy a 5 pound bag, it's automatically $35. So this is broken up. So when calculating the cost, the result can be any fraction of a dollar or cent, and therefore it is continuous. However, because the smallest unit of currency is only a penny, then you're not going to want to say that this costs 0.011111 cent. We're going to round to the nearest cent because money is only, we can only have 1 penny. We don't have a half a penny. So think about that when you're doing problems like this. Make sure that it makes sense in terms of the problem. All right, so I would like for you to complete the lesson check in your workbook. It is at the top of page, let's see here, top of page 8 in your workbook, and we will go over those answers in class once you complete them. So I do expect you to be working them out. Okay, and we're going to keep on going. We're almost finished. We're going to look at some set builder and interval notation. I always teach both in my Algebra 1 class. I don't know if every Algebra 1 teacher shows you both interval and set builder notation, so if not, that's okay. You're going to learn it now. We're going to discuss it together. So set builder and interval notation are ways of it's two different ways of saying the same thing. You can say there's 6 or there's half a dozen. 2 ways of saying the exact same thing. That's exactly what this is. You may remember me talking about interval notation, and then I call set builder the fancy pants notation. I feel like I have to talk in my fancy voice when I use set builder notation because it is X such that X is from here to here. I just think it sounds more sophisticated, so I always use my fancy pants voice when I'm talking about set builder. You may remember that from Algebra 1 if you had me. But we're going to look at this. Set builder, sets of numbers like the domain and the range of a function can be described using various notation. Set builder notation, interval notation, and algebraic notation are all concise ways of writing a set of values. So we're going to tap on each one. We know algebraically that this starts at 2. It's an open circle, so we're not including 2. We do not want the equal to, but it's all the values less than 2. Okay, here, if we look at this one, this is x, such that x is greater than or equal to -2. It's a closed circle, so we include -2 and everything bigger than -2. If we look at this one, we have a break in the graph. So we're going from -infinity up to 0, or all the values of x that are less than or equal to 0, and we want to make sure we include that 0. Then there's a break. Or we have all these values over here that start at 2 but don't include 2 and are greater than 2. And this looks like an and problem because it's linked together. So it starts at -4, doesn't include -4. That's why we don't have the equal to under there. It does not include the -4, but then it goes all the way up to +4 and includes that +4. So this is what it looks like algebraically. So in our set builder notation, we have x such that x is less than 2, not including 2, but everything less than 2. I know I'm a total nerd, but that's what it makes me think of. It reminds me of going to McDonald's and ordering a parfait or ordering the filet mignon. Mrs. Blevins is a very simplistic person, and this reminds me of being fancy and not very simple, but it's out there. I've got to introduce it to you. So here it is. So we have x such that x is less than 2. We have x such that, this line, that straight up and down line just means x such that x is greater than or equal to -2. With the or problem, we just write the or in there. With the and problem, we have to make sure that we smush it together. And then we've got x such that x is an element. This fancy little e thing is called the element. It's the element of the real numbers, of all real numbers. That fancy r means all real numbers. All right, and interval notation, this is my preferred method. Some people don't like it, but it's what I prefer. We start at -infinity. This is the -infinity symbol, and we go up to 2. We're not including 2, so we use parentheses. Here we have a -2. We are including it, so we use a bracket, and we go all the way up to +infinity. You can't include infinity because it's not an exact number. So I can't say I include it and put a bracket there. I have to show it that it continues on forever. It can't be included. Therefore, I use a parenthesis. And this one has both. I go from negative infinity, not including, so it's a parenthesis, up to 0, including 0. So I'm using my bracket. Then there's a break. So I have to union that with the solution set. I've got all these solutions and or all of these over here. It could be all of these or it could be any of these. So I say or using the union symbol. That's a U for union. So unioned with 2, not including, so I'm using my parenthesis, up to +infinity. Okay, and I could keep on going through these, but you get the idea. So when I'm using set builder notation, it's important to recall that integers is represented by fancy Z, natural numbers are represented by this fancy N, real numbers are represented by the R, and rational numbers are represented by Q. All right, example 6. Let's try this one together. I think I told you guys wrong on that page number on that last one. It was at the top of 7, and I think I told you it was, I don't know what I told you. I can't remember that far back. That's been too long ago. All right, so example 6. Tap on each button to write the domain and range of the graph in set builder and in interval notation. So with my domain is all values of x. I can see that this is a continuous function, so it's everything. So it's going from negative infinity all the way up to positive infinity and everything in between. So we can say that x such that x is an element of the real numbers using my fancy pants or set builder, as you may like to call it, or we can use what I like to call plain and simple interval notation. We're going from negative infinity all the way up to positive infinity. But let's think about our range. Our range is our y values. Am I including all real numbers on the range? No, I'm not. We can see that my range never goes below this value of -6. There's no points below it. It goes up forever and ever and ever towards positive infinity, but it does not go below this -6. So my range then is going to be y such that y is greater than or equal to -6, or we can say it includes -6, so I'm using my bracket, and it goes all the way up to positive infinity, and we cannot include positive infinity. All right, let's look at example 7. And this is our last example for the day. So write the domain and the range of the graph in set builder and in interval notation. So my domain, it looks like my domain is all real numbers except for everything in between 0 and -1. See, there's nothing here on my graph. We include 0. We do not include -1. So the domain is all real numbers less than -1, but not including, or all real numbers greater than or equal to 0. So we say x such that x is less than -1 or x is greater than or equal to 0. Now notice, I'm not including the -1, so we have to use a parenthesis to show that we're not including. We can never include infinity because it's not an exact number, so I have to use parenthesis again. They used a bracket at 0 because I am including the 0. Okay, so my range then, what is my range? Looks like range is everything less than -1, right? We have a range value here at -1, but not including that one because it's an open circle. And it's everything greater than 2, and it's including 2, so it's greater than or equal to 2. So we say y such that y is less than -1 or y is greater than or equal to 2. Once again, we're not including the -1, so it's a parenthesis. We are including the 2, so it is a bracket. Let's check our answers. Woo woo, we got them right. This is why I really like this resource for you online, because you can go on and try these extra examples that I'm not working out with you, and you will immediately know if you got them right or wrong, and you will know which part you got right or wrong, and so then you can better understand it. So I would like for you now to complete the lesson check in your workbook at the top of page 8, and I will be checking that in class. So that is all I have for you guys today.